Thank you for the nice introduction. So I'll give today an overview over different components of visual recognition. So today, visual recognition has made a lot of progress. There are many applications, things which do work now. For example, face detection is in cameras. It's the first step for face recognition. There is things on your smartphone where you can search for particular objects and places. But then there's also a lot of things which still don't work. So if you want to describe the complete story of a video, so for example here, as the head waiter takes them to the table, they pass by the piano and the woman looks at some and so forth, we know all that's something which is very far from what computers can do today. They can maybe detect the person, understand maybe some of the objects, but it's clear that they cannot narrate the story. They cannot capture what are the intentions, what's going on in the video. Okay, and so what are the important components for today's machine vision perception? So one is machine learning. Obviously, everybody knows that machine learning, in particular deep learning and weak supervised learning, has become very important. And then the other thing which is very important, maybe even more important, is the data, right? So basically, you have to have some data to learn from this data. And there's obviously a lot of data online, but what is the quality of the data, right? There's a large quantity, but the quality is not always that good. And so basically you can make the difference between manual annotation, which is very tedious to obtain and not always good enough. And then more recently people have looked at how to do weakly supervised annotation and how to use synthetic data. And then once you have these two components, you can then design actually models for machine visual perception, where then there you use the knowledge of what is actually necessary to understand the world and how to design more complex models. Okay, and in this talk, I'll first explain some of our recent work on data, so weakly supervised learning and synthetic data. Then I go to our recent line of work on how to understand videos. And then in the end, I show some recent work on interaction with the real world based on the robot manipulator. Okay, so first of all, there's a lot of annotated data around. So people, and in particular companies, they annotate as much data as they can. For example, there's the open image data set. There are almost 16 million bounding boxes for more than 600 categories. There's the AVA data set for actions, where there's like 80 atomic actions annotated in more than 400 movie clips. But then what is the issue here? Obviously you can annotate more and more, but it's very time consuming, you have to pay for it. But then also the problem comes up, what is actually the right vocabulary, right? So basically you have to fix vocabulary. In particular for actions, it's really hard to fix the vocabulary precisely because you have many different types of interactions with objects, interactions within people. Then you have not long-tail classes for which you have not much data at all. And then in some cases the information is very difficult to annotate. So for example, flow or 3D body shape, it's very hard to annotate. So there people actually have to go to synthetic data to get some initialization of the approach. And so this leads me to our first line of work where we have actually created synthetic data for humans. So this is the surreal data set. And so here, what's the rationale is basically if you want to annotate human shape, 3D pose, and even more so body shape, you cannot do this automatically. And so here, what we do is we design this synthetic data set to obtain the data for this synthetic humans. And so what we have a set of people for which we have the 3D shape, which is obtained by scanning the data in the scanner. And then we have 3D pose information for mocap data. So that's mocap data where you measure how people move in the scene. And then once you have this data, you can generate these sequences of humans which move. And then you can generate a lot of different types of data by changing the lighting condition, the camera position, and the background clothing and the scene, right? So basically once you have these people who are moving, you can change them many different ways. You change the viewpoint. And then what you have for this data is you have the 3D pose, the 2D pose, the part segmentation, the depth, RGB normals, and body shape, right? So you have all the information, and you can then use this to train your system. And in the long run, where we want to go with this is not just have these people, but also have them perform complete actions. So once you have them, you can really then go towards having them perform actions and use these actions for training. And in here a bit more detail, what we have the Caesar data set for human body shape. So it's a data set of human bodies which were captured in the scan room. We use for now static images as background, this L-SUN data set. Then the CMU data set for mocap sequences, and then we can really generate this very large set of training and test clips. And so here, just to show you an example of our data set, you can see here on the left, it's the synthetic data. So you can see that one thing which is still missing is to have the humans walk around real scenes. So what they're doing now, they're superimposed on 2D scenes, 2D images, but you can see that the quality of the humans in many cases is very good. And it's actually almost realistic. So you have this realistic texture on them. So the texture is obtained from real images, and it's just like recombined to put it on the humans. And then you can see that for this data, we actually have real ground truth. Okay, and then to see how we can, if we can use this as a first approach, we just took the stacked hourglass network, which is a state-of-the-art network with several layers for segmentation and pose estimation. And what we do there is we outputted different channels for different segmentation masks, used our synthetic training data as input, and then measured and compared the performance for different variations of real, synthetic, and real. And so then to test, we tested on the human 3.6 million data set, which is a real data set, but people move around this mocap room, so we do have actually the precise body shape and the annotation. So you can see here, basically on the top, the input image. Then if you train on real images, the performance of our segmentation masks. Next, we train on synthetic images, and then real and synthetic, and then the ground truth annotation, which you obtain actually inside this mocap room where we have many different cameras. This is a state-of-the-art data set, it's not our data set. And you can actually see, so measuring IIU, it's intersection over union of the segmentation masks, or accuracy. What we can see here is that basically real, if you have a large amount of real data, it performs slightly better than synthetic data, but you can see that synthetic annotations performs also very good. So the gap is really very small. So synthetic data is actually almost good enough to obtain the same performance as real images. And then if you combine synthetic and real together, you get a large boost in performance. And obviously the boost in performance is the larger, the less real data you have, right? So this is something which applies if you have only a few examples which are labeled on the real data, then basically the performance is really very much better if you add the synthetic data. And then just to show that the approach actually works well, even in realistic environments, we just run our approach on the YouTube post data set. So these are clips from YouTube where people are actually, they're centered, but they're performing different actions. And you can see, again, that our model just trained on synthetic data performs still very well. And then the next step we wanted to show, actually, so this is just a proof of concept that the synthetic data helps. And then the next step which we took was actually now what we wanted to do is use the data to get the full 3D body shape out, right? So now we have the synthetic data for which we have the annotations, the images, and the output, the full 3D body shape. And so you can actually use this to train going from single images to 3D human body shapes. And so what's interesting here is in our approach, so we go from the image to the 3D human body shape. But what we add, in order to add some realistic data, we add annotations for 2D segmentation loss and 2D pose loss on real images. That kind of makes our approach adapt to real data as well. So it takes at the same time real data and the synthetic data for 3D shape. And then the other thing which we found was important to have the reprojection loss, so not just compare in the standard normalized frame, but also turn the humans and see how the volumetric losses evolves over different poses. So then basically you could see that by doing this, we could obtain state-of-the-art results for 3D human pose. And so basically now with this data, we can actually have this 3D human pose. And then more recently, we also looked at if we could use this to model the interactions between hands and objects. And so there, actually, synthetic data gives even better results because hands are pretty easy to model in synthetic data because they don't have much texture. They're pretty straightforward to obtain synthetic models for the hands. You have techniques, so what we use here, techniques such as domain randomization, so where we add different variations to the synthetic data. Then the same thing for the objects. We can also model the object shapes based on ShapeNet. And then basically what we can see here, we can really learn how to manipulate objects, like to get from an image the 3D shape of the hand and the object, see how the hand grasps the object. And so this is something where we can show that the synthetic data gives really good results. And the second thing is where we're going to go with this is to see actually how to model interaction. So this could be something which you can then apply, for example, to train a robot if you want to see how the human hand interacts with the objects. And so this was our first line of work of using synthetic data. I think this is something which is going to be more and more important as pre-training, as generating additional data. Once you have a good model, you can basically generate any kind of variability for the synthetic data. And then the second part is obviously weak supervision. So on the web, you have a lot of examples where the videos or the images come with text, speech, additional annotations. And obviously, we can use these additional annotations for training. And so here, I'll introduce one of our very recent approaches, which will be published at ICCV this fall, which is actually learning for multimodal supervision. So the model is called Video BERT, and what it does, it learns from video and the corresponding ASR. So ASR stands for automatic speech recognition. So what we have, maybe just to show you here, is we have as training data cooking videos. So on the web you can find a lot of these different cooking videos, and all these cooking videos people actually say what they're doing. So they kind of say, I'm putting this thing on the cake and so forth. And so basically then you can use automatic speech recognition to transcribe what they're saying to text, right? So what you have now, you have this video data with corresponding text or description, which is relatively good and kind of captures the content of the videos. Okay, and so what we want to do is to learn from this video in ASR. And so, I don't know if you're familiar with the recent BERT model. The recent BERT model is a language model which learns the dependency between words and sentences. So it's a way of pre-training language features, which gives currently state-of-the-art results based on transformers. And here, the idea is to use this model, but to generalize it to learn the correspondence between video and speech. And here we apply it to domain with sufficient training data. So here, cooking videos. So here we learn actually the correlation between video and speech for these cooking videos. So here we already explained our corpus. So what we have is we have 300,000 videos from YouTube. They're more than 1,000 days length in total, and we have ASR output for them. And so in more detail, what is the model we're using? So here we have this Video BERT model. So maybe if you just look on the left, that's just the language BERT model. And what you do is you take as an input a sentence, and then you mask out some of the words in the sentence, and you try to predict these words. And by having this loss function which predicts these words, you actually learn inside this transformer the correlation between the different words. So what you really learn is you learn how these words correlate and what is the longer range structure. So it's like similar to word2vec, but it's a better way of learning these features. And then what people take is they take these features before the penultimate layer and then pre-train as a pre-trained feature vector and then adapt it and use this for language. So what we do here is we concatenate the sentences with the video clips. So what we have these videos, these long videos in which we have sentences which describe the activities inside these cooking videos. We take the sentences, we have the matching between the videos and the sentences because we know when the people are speaking, and use this to chunk our video into like stacks of frames and corresponding sentences, right? And that would be a stack of these frames, and the corresponding sentence would be the input to our Video BERT. And then the question is, how do we obtain now these words in the video, right? You just have a stack of frames, and we need to have something which resembles words. And so what we do here is first rely on what we know are good video features. So what are good video features are C3D features, so 3D spatiotemporal correlations, like convolutional filters, right? So instead of doing convolutions only in the image, we do them in 3D. And so we apply these standard features, which are pre-trained on kinetics, to chunks of 1.5 seconds of video, right? So for each of these 1.5 seconds of video, we get like one feature vector, 1,000-dimensional feature vector. So each of these clips is presented by 1,000-dimensional feature vector. This is just the architecture of our 3D convolutional network, which we use here. And then once we have that, we get like these continuous features, right? We get this, like say the clip is like 10 times 1.5 seconds. We get 10 different discrete continuous representations. And now to make these representations discrete, we have to have in addition a clustering approach, right? So we have to do clustering. So what we do here, we have hierarchical k-means, whatever. And so this allows us actually to cluster together similar, like for example, these two cakes are clustered together. So what we get is like similar things which are similar in appearance, right? And so this, then we take the same parameters as for the language. For language, there are 30,000 words. And for our video, we also have this 30,000 visual words, right? So this kind of gives us a discretization. And then again, we can mask out these words, predict which of these cluster centers we should have, and then train the whole network together end to end. So basically then we learn how the video features like are temporally correlated, and we also learn the correlation between the language and text. So we can then show that basically the video features improve and the cross-modal learning is there as well. So we can show that there we learn how to correlate the language with the video. Okay, this we've seen. Okay, and then two applications are the first one. We actually show that we learn the correlation between video and language. So what we do here, we show that we can do zero-shot action classification. So we can take a separate data set with no overlap, which is actually UCOOP2. And for this UCOOP2, we feed the video features into the video BERT model. And for the language, we just say, now let me show you how to mask the mask. So basically, we mask out what's going on. And then we want to predict what actually the nouns and the verbs are, right? And so here on the top, we see the first three nouns, so make, assemble, prepare. And the nouns would be pizza, sauce, pasta. So it actually has learned the correlation between the video and the text very well. The bottom, another example, make, do, pour. And the nouns are cocktail, drink, and glass. And then if you look at an evaluation, so as I said before, we have this UCOOP2 data set for which people have actually annotated the verbs and the objects manually. So what we can do is we can just take our 3D convolutional features and fully supervised approach to train. So that's the top row. So we get like 46 and 30 for verbs and objects. And then we can use our video BERT model, which is completely unsupervised, right? We just take the videos from the web and you don't annotate anything. And we can actually see what is very nice, that the performance is comparable. That's quite surprising. In one case, it's fully supervised. In the other case, it's completely unsupervised. And then the second thing, which is very nice, is that we can show here on the right, that by adding more and more data, actually the performance of our approach improves. So we have recently added the how-to 1 million data set to this 300K video. So that's something which was developed in another group at Inria, and you can then show that the performance goes further up. So you can really see that this model is very powerful because it has these many parameters, and that's why they showed the language. So the more data you can have, the more you learn these correlations. And then recently, so I don't have it here, but recently we have also looked at the video features, and you can also show that the video features by themselves, they also improve the performance over just having an average pooling of these standard C3D video features. Okay, so this was the first part of my talk, so basically showing that synthetic data can be very important, and then weak supervision is in the long term going to be more and more important because we cannot afford to annotate every and each concept in the world. Even if you're a big company and you have a lot of raters, you don't want to do that, and it's just like too difficult in particular for actions. Then so the second part is on video understanding. So what are the motivations? Basically, what we want to do here is to go away from the additional clip classification, and you want to really understand, as I said in the beginning, what's the content of the video, right? And this is two applications where it becomes completely obvious. It's for self-driving cars. You have to see what the person is doing, where the person is. Is the person crossing the street, or is the person standing there? What's going to happen? And then similar in video surveillance, you want to see what are abnormal behaviors, what is actually dangerous, what is not dangerous. And there again, you need to not just classify the full scene, but you really have to see where in the scene the people are performing the actions and what the actions are. And so how are we doing this? So basically here, what we want to do is we want to localize the people in this video volume, and then we want to localize temporally where precisely they're performing the action. So for example, on the top, we see this drinking action, and we really want to localize the instance where the person is drinking, right? And then similarly here, somebody is brushing their teeth, and so again, we want to see where in the video the person is brushing the teeth. And then people have been looking into the spatial temporal action localization for a while. And so initial approaches, what they did, they just looked at the data frame by frame. And so basically then for each frame, instead of doing object classification, they did action classification and had, like, for example, one of the approaches from Georgia and Jitendra was actually to say, this is the use faster RCNN to predict the actions. And then basically once they had the actions predicted frame by frame, they could then track these actions over the video, link them together, have some temporal sliding window mechanism which says where precisely this action is performed, right? So to show really what is the extent of the action, and then predict this action classification. And obviously, this is suboptimal. We have seen this before for the video bird, but here we can see it again. So basically, if you look at this frame, the person, we don't know if the person is sitting down or standing up, right? So it's really unclear. And what we would need to have is to have the context information telling us if the person is sitting down or standing up, right? And if you have the frames around it, you can actually see very well what's going on. So you really need this information, this temporal information, and not just look at individual frames. And so there has been now a number of approaches which take into account this 3D information. And one of the approaches is here, which is relatively straightforward, is we apply faster RCNN to localize the initial regions where the humans are present. And then on top of this, so this gives us the human bounding boxes here. ResNet 50 gives us the region proposal network. So this gives us an idea where in the individual frames the humans could be. And then on top of this, we apply these 3D convolutions, which measure how the human action is performed over time. And we can do this. So one trick is to do this in appearance and flow. So flow is kind of complementary information to appearance, right? So appearance, you just see the RGB. In flow, we have an additional information how the person is moving. And obviously, if you have these 3D convolutions, you could say that it should extract flow at the same time as appearance. But for now, in practice, it's better to first extract the flow and combine it with the appearance. That gives you a small boost in performance. But obviously, in the long range, probably these 3D convolutions can obviously also be trained to predict the flow correctly. And then once you have these two streams, you can use them to classify the individual frames in the video into performing the actions by looking at the neighboring frames, right? So here, you don't just concentrate on one frame, but you have this long range, relatively long range, where you look at what the actions are performing. So I won't go into any results in detail, but just show this video where you can see in green the ground truth and in yellow the detections. And so the labels here, they're all correct. So basically here the person is high jumping. What you can see actually is that A, the person is localized correctly, given that you have trained, supervised training, that you have trained on these actions. You can actually, even in the presence of strong motions, you can detect and predict the location precisely. Here, for example, in skiing, you can really see what it does. It's localizing the person in the frame, then predicting that the person is skiing, and then linking this track over the video, right? And so basically here, given that it's supervised, you have really learned these different poses for the different actions. You can detect them very precisely and then link them together. Here it's like jumping on a trampoline. And so one thing, okay, now the failure cases. So one failure case here would be that it's sometimes hard to predict the precise temporal localization. And the second failure case here is that you have several people interacting, and then basically the approach fails, because for now it's just focused on one human, and what you would need here is a model which either measures how people interact together or have a more complex model which actually goes down to a more precise representation, not just this bounding box representation. And the failure case before was a temporal localization, which is also very difficult. So in some cases, if the actions are short or not completely discriminative, it's hard to precisely localize the actions in time. And what these measures do, they say that you have to localize the person, the action, and the temporal extent, right? So they have this IRU measure in space-time, and if the temporal localization is not precise enough, then it counts as a failure case, which makes sense. And the second thing which you can see here by watching this video is actually that the current data sets are very simplistic. So they're all like very simple, small data sets with sports videos, which are obviously quite easy to classify and to detect, right? You just have one centered human. The context helps you a lot for detection, classifying the actions. And so what we have been doing is we have put together this data set of atomic visual actions. And so what we have here, the idea was to take 15-minute-long videos and annotate each and every human and their corresponding actions in these videos. The second thing is we put up this definition of atomic actions. So basically, atomic actions, the idea was to have a vocabulary of relatively basic actions which you could annotate and then maybe combine together to get these more high-level actions. Okay, and so if you look at, and then the last idea is to say that each human in general doesn't have just do one actions, but in general often you do multiple actions, right? So you sit down, and at the same time you talk, or I stand, I make some gestures, and I give a presentation, right? So basically, and these things you actually want to annotate to be exhaustive. And so here, if you look, so here the woman on the left is sitting, talking and watching, and on the right she's kneeling, listening to and watching again. Then here another example, read, hold, and so forth. So basically the actions which we have are categorized in several categories. One is the pose of the person. The other one is how the person interacts with the world, so carrying an object. And the third one is the person-person interaction, shaking hands. And so that's kind of the different categories which you have in this list of atomic actions. And then if you look at how this model, which I previously introduced, performs on this AVA data set, you can see here that, so the one which I showed before was this UCF 101 24 categories data set. And you can see here two things. The performance on this data set is very good, so 80% accuracy and MAP. And if you look at what's interesting here is by adding more and more temporal information, you get actually a boost in performance, right? So basically here, if you go from 1 to 20 frames, the performance improves significantly. And then if you look at our AVA data set, the performance is relatively low. So this really shows that basically these toy data sets are much too simple, and we need to go to more realistic data sets. And so maybe in a nutshell, what are the problems here? Why is it so low? So one thing is that you have these multiple actions which can occur for one person, which makes it harder. The second is there's a number of long tail categories. So basically we have just annotated the actions in 15-minute-long video clips, and some of them don't occur very often. For example, swimming is an activity which people actually don't show much in videos or movies. So basically you don't have many swimming annotations, so then the performance drops. That's second. And then the third, what I said before, the model is relatively simple. So for now, it just concentrates on the human, right? It doesn't take into account the interaction with the environment. So the first thing we have looked at is, can we actually model how the human is interacting with the environment? So here, for example, we see a false answer for handshake. So the guy, it looks like the guy is shaking the hand of the other person, but in reality, he's reaching out the arm. And to find this, you would need to look at the second person, not just concentrate your attention on one box, right? So now we're just classifying this one box. And then the second false answer is false answer for smoke. So basically looks like as if the guy was smoking, but in reality he is covering the mouth and has no cigarette in the hand. And then this third one is false answer for writing. In reality the guy is looking down and eating. So basically again, you would need to detect that the environment contains a table. And so what we have here then done, and that's where this component of modeling actually what would be a good model for understanding the visual world is we have designed a model which takes into account how these actions evolve over time, how the people interact with the environment. So to get this environment representation, what we do is we extract a number of proposals we link the actors to the proposal in the environment, and then we determine in a weakly supervised way which are the relevant objects for the action. And the second thing, so this would be the stream for the object detection, and the second stream, what we do is we have our actor. We want to see how this actor evolves over time. So for example, if somebody is falling down, then the interaction would be different than if he's like just sitting there in the middle. And so there we use graph convolutional network to model how this person is evolving over time. So this network, this graph, where I have the links, the nodes between the people, like the appearance of the same person, evolving over time, and then the interaction with the environment where we link this person to the different objects which are in the neighborhood. And so in more detail, how do we get these actor tubelets? So the actor tubelets, we first detect these actors in the video, and then we link them together with a relatively simple similarity measure based on Siamese networks and triplet loss. So we learn how, if the actors are similar, we use that to link them together, and this gives us these short tubelets. Once we have these short tubelets, we actually learn how to combine the individual. So we have these individual C3D features, like 1,000 dimensional C3D features, and we learn how to combine these C3D features with graph convolutions. So we really learn how this action evolves over time. So don't just do average pooling, what people usually do, but learn how this action performs over time. And then this is the first thing. And then the second thing is we have this graph-based modeling where we look actually what are the objects in the environment of the human. So it could be human-human interactions or human-object interactions. And this is completely weakly supervised because we don't annotate. And then we use soft assignment to integrate these features. Right? So this gives us like a representation which learns on the fly which are the relevant objects in the neighborhood. And here I show two examples. One is showing the benefits of modeling temporal dependencies. So the first one is the baseline. So this is just average pooling these C3D features over our tublet, right? In blue that would be the tublet, and then basically what we have here, we have the incorrect label sit. So basically just latches onto the middle frame and thinks that the person is sitting. And then on the right, we follow the person and have a correct model of the person. And then we learn that basically what's important here is that fall down. So we have to give more information to the way the person is falling down, right? So basically that would be then more important, and then we can actually model correctly and label correctly this fall down action. And then the second point was this modeling of relations. So we can see here on the left the person is classified as holding, but basically it's actually not incorrect, but he's holding a fork. And then basically here the relational model then learns that the fork is important for the action, and then we can actually label the action as eat, right? So in what we have in the beginning, when we learn these different objects, we have the label eat for the action, but then it determines automatically what are the important objects, like with the soft labeling, in the weakly supervised, what are the important objects in the neighborhood for eating. And so basically if you have the label eating, then you can learn that the fork is important, and once you know that the fork is important, then the label, if you don't then apply the model to a test video, then you can really predict that the person is eating. And then if you look at the results, you can see that by adding the soft relations and the soft tubelets, we get a 6% improvement. So you can get a relatively important improvement, but you still see that the performance is relatively low. And so the thing we're now looking at is this long tail distribution, which has a very large impact actually on these classes which have low performance. So we have currently classes which have almost close to zero performance. And so there, the difficulty and the issues are how to get these automatic labels on the fly, right? How can you mine through these large collections of video to find additional data which you can then use to train this long tail, these classes automatically? So there again, we have to go back to weak supervision because we cannot just annotate all and every video data, right? Basically, if this action, say, fall down, doesn't appear very often, it appears once every 10,000 frames or 10,000 videos. You cannot just label every action. So what you need to do is to do some predetermined mining or some features which help you to pre-localize the parts, the chunks where the action is likely to appear, and then you can use that to annotate or to see how to use that. But there's no way of annotating everything. So this is like another problem with these long tail distributions, which I said in the beginning. That's why we cannot just annotate the full visual world. Okay, and then one thing which I mentioned in the beginning is also what we also would like to do is future action prediction. So we don't want to only label what is currently happening, but we would also like to say what are the next steps. And obviously you're going to tell me you cannot predict precisely what's happening because you never know. If you look at somebody, is the person going to sit or stand up? But there's like a probability that somebody is going to sit here, is not going to jump up immediately. So you have like a probability of predicting what the next actions will be, right? And so basically what's important here in our model is we take into account the structure of the scene and the actions to the predictions, and then we can also have some kind of likelihood if the action will be appearing or not. And so here, if you look at this clip, so what you have here, they're sitting and talking, and the next thing would be clinking glass. It's kind of pretty obvious for you if you look at it, right? And then here, again, person is standing and holding. Next thing would be serving. And then here, hugging and standing. Next thing is kissing. And then, so here, the model we're using. So here, again, we've designed the relatively complex model. So the idea is we have the past and the present. So we have the present frame. We know what has happened before. And then what we want to do is to predict the future. So here, in this example, she's riding the horse. Then she's stopping and talking, and then the question is, she getting off the horse or not? And so in this case, she's getting off, and it's kind of likely because the guy stops the horse, and then she's going to get off. And so here, what we found important again is not to use the features, the average pooled features which are there before, but to take into account again to have this relational model, which learns it's a different relational model, but here, which learns in a weakly supervised way again what are the context features to really see what is the context of the action, what is the scene around, who are the people around, what is the object around. And then here, in addition, what we have here is an RNN, so basically based on a GRU, current graphical unit, which predicts then what is going to happen in the future. So with these two components integrated, we have the structure of the neighborhood, and then this concurrency measure, which predicts what's going to happen in the future. And then here you can see the prediction. So here we predict that the person, what we see as input, we just see this frame which is on the left and the frames which were before. And then we predict correctly that the next step, which is the person is doing, is going to eat. And then here we predict that the boy will get up. Again, it's correct. And here, again, when we only see the left frame, we can see that she's going to read. Here, the person is going to open the door. And then if you look at two failure cases, so here we can say we predict that the person is getting up, but in reality it looks like the person will be getting up, but he's not getting up. So this is actually basically a wrong duration. He'll get up later. So what's here important is to predict that you have several predictions for the future, right, and not just one. And then the other one is close the door. Instead, the person is opening the door. And as a matter of fact, if you just look at the left frame, it's unclear if the person will be opening or closing the door. And so here again, it's very important that you predict not only one future, but multiple futures. And so what's different here from previous approaches always use segmentation masks, or almost always use segmentation masks. And here we really go to the interaction with the scene and have a full model on the scene. And I think this is kind of important for future work in this area, is to really understand what's going on in the scene and not just have a very low-level representation of the scene, because then you just can predict on a pixelized level and you cannot really measure and learn how people are interacting with the environment. Okay, and so in my last part of my talk, I'll present some very recent work. So recently I've started to look into how to interact with the real world. And so basically the tenet here is that if you want to go to next level AI systems, you have to not only understand what's in the videos or in the data, but you have to also interact with the environment so that you can basically learn by exploring the world. Well, this turned out to be a little more difficult because basically just setting up a robot manipulator, getting it to train, perform simple actions is harder than you think. And then basically, if you really want to learn the appearance and the texture of the models, it takes a bit more of an effort. But anyway, so basically what we have started to do is to put together an approach which learns this long horizon manipulation. So here you see an example. What you want to do is you want to make a meal or a breakfast. So basically have different bottles and cups on the table and pour them into the dish. And standard approaches in robotics, they are either doing imitation learning and reinforcement learning. So imitation learning, what you have is you show an example, you demonstrate an example, so the robot performs the action, or in simulation, somebody performs the action in simulation, and then we can learn how to do this task. And this is easy for short tasks, if you have a lot of demonstrations, but you cannot go beyond the demonstrations and if the setting is exactly the same, if you don't have any changes of the objects or anything. And then the second line of work is based on reinforcement learning. And so what we found is to teach a robot with this many configurations with reinforcement learning. And as far as reward to perform a very complex task just blows up your complexity to infinity, right? I mean, if you have many steps, it trains for hours and hours and hours, and it never actually converges. Especially if you have a sparse reward. Sparse reward means just, in the end, you want to see if you have assembled your meal. And so the approach which we have proposed recently is to combine reinforcement learning with behavioral cloning, so imitation learning. So we first learn a set of simple skills, for example, grasp, pour, go to summer, and then on top of this, we have a master policy which learns how to combine these different skills with reinforcement learning, right? So basically you take as input the set of skills, and then reinforcement learning learns how to assemble these different skills in the right order and in the right way to combine them together. So what it has as an advantage, so maybe two things. The reinforcement learning allows you, has these steps. You perform one task for n steps. If it's not completed, you go over it again. So basically, it's very robust to failure. So if you don't manage the first time to grasp your object, it will go back there and retry to grasp it again. And then the first thing of the skill learning, what this helps you to do, I'll get back to this in a moment, but basically it helps you to be robust to variations in the object or the position of the object. And so basically overall this approach is sample efficient, and it's easy to do reward shaping. And then just now, in a few words, how do we do this imitation learning? So we use behavioral cloning. So behavioral cloning means that you show the robot a set of demonstrations and you learn from them. And so what do we do here? We have our simulator. We do an action in simulation. So in simulation, we have many examples of the robot arm grasps the cube. So that would be like one skill. Robot arm goes and grabs one cube. This gives you a set of input images, right? So here, what we take stacks of 3 depth images, 3 consecutive depth images. And from these 3 consecutive depth images, where we see where the robot is, we can then output the action. So the action would be the velocity and the angular, the linear velocity and the angular velocity of the robot arms, the different ones of the robot arm, and then the position of the gripper. Okay? And so once you have this training set, what you do then is you train a CNN to predict, take as input these 3 frames, and as output the policy of how to control the robot. Okay? So this would be this pi of OT. OT is the input frames, and outcomes, this is the control policy, outcomes, how to control the robot. You use a general L2 loss to minimize this whole system. So this is just a CNN trained end-to-end. And what we found very important here is actually that we use a lot of expert demonstrations in simulation. They're recorded from different viewpoints. We use, as in computer vision, data augmentation for the sampling. And then it's also important that you use the right architecture. So we use here ASNet 18, and we showed that that outperforms significantly the other architectures. And so then once you have that as input, basically the trained configuration can grasp different objects, right? Because now you have this generalizability of CNN. So basically you can I'll show this in a moment, that you can not only grasp a cube, but you can also grasp an apple and orange, even though you have never seen it. And the second thing, given that we show many different inputs, the system is also robust to different positions of the gripper and the object. So it really learns to abstract above the precision and the gripper. And then this is trained in simulation. So the question is, how can we now go to real images, to real environment, basically? So what we have, the arm is modeled in simulation as the real arm. But then if you look at the depth image, it's quite different from the real depth image, right? And so what we have then done, we have built up on recent work of domain randomization. So the idea of domain randomization is that you add a lot of noisy data to the initial training set, right? This is something which is used in robotics, but also in computer vision. It's one of the ways how to go from simulation to real. And so what we have here is we have our synthetic data set, and we have one proxy task, the position and the cube of the cube in the real world, and we use that to define our data augmentation. And you can see here how, and then we have some kind of mechanism based on Monte Carlo tree search to perform in an intelligent way the selection of the different images we use for data augmentation. And here you can see what type of different transformations we have used here for this example for data augmentation. So cut out, erase the object, add white noise, add noise on the edge. So it's kind of important to add this noise on the edge, which appears in usual depth images, scale, salt and pepper, and then sharpness. So we have all this different, and then we can show that by just using this one proxy task in the real image, we can then go directly from simulation to real. So we just have to train in simulation. And then once we have trained all these different skills, which now work on our real robot, the question is, how do we combine them? So we have like a set of these individual skills, and now our RL algorithm learns how to put them together, and then switches between skills every n time steps. And then basically if the skill is not performed after n time steps, it's kind of redone again, okay? And so we have another head in our CNN, like a set of heads for the skills, and then one head for the master policy. The master policy is trained with proximal policy optimization, one of the recent RL methods. And then for our experimental evaluation, so we have two complex tasks. One is putting an object into the bowl, and the second one is what we call Euro 5 breakfast. So our arm is Euro 5. Breakfast means that we first pour things from a cup, then from a bottle. We have different ingredients, pour them into a bowl. On the left, you can see the training set for simulation, and on the right, execution on the real robot. And here, just to give you an idea of the skills which we train with behavioral cloning. So skill would be go to the cube, go down and grasp, lift the cube, go to the bowl. And then in the salad thing, we don't have skills for the individual objects, but we just have go to the cup, go to the bottle. And then once we have gone there, we just grasp the object and pour, and then release the object again. And these are the skills. Then they're put together with RL. And now we can see a few examples, how it performs on the real robot. So this was all trained in simulation. And so here this would be pick up the object, put it in the bowl. And what you can see here is actually we show which of the features in our convolutional map light up. And we can actually see what it learns. It learns where the object is, and this gives the system a strong cue. And then here, unseen objects. So it can actually generalize to unseen objects. We have trained on a cube, and then here it generalizes to these objects. You have seen if it doesn't manage to pick up the objects immediately, it really executes the skill again, and then based on the RL, and then puts it in the bowl. We can also generalize to new object instances. So we have a set of bottles and cups in our training set. So they come from ShapeNet. So we split ShapeNet in 50 training and 50 testing bottles and cups. And you can actually see, as you would expect from a detector classifier, that you can then generalize to unseen cups. So we haven't seen any of these cups or bottles in our synthetic training set, right? And they haven't seen them in reality either, right? So they're just like, they're learned by the CNN by generalization. So here we can then see we have these two objects. It pours into from the bottle, and then it pours from the cup. And then one thing which I said before, because our skills, they're trained with different positions and different configurations, we can actually move around the object, and basically, given that we have the visual input, we can then adapt to the new position. And then one thing which is very nice, we're also robust to occlusions. Given that we have this RL, it kind of sees that it's not able to execute the task, and then you can actually wait till the occlusion goes away and then still execute the task. And so one of our baselines was, instead of having a RL on top of the skills, we just used the skills in the predefined order. We just said we have the skills, and manually we could obviously order them, right? And then we compare our RL policy on top of the skills with just this ordered policy. And you can see that if the objects are close together, it doesn't learn which objects to grasp first, and it just pulls over the bottle. So you can actually see, in this case, this ordered policy fails. So basically, the two policies perform well. If everything is simple, everything goes well. But then if you have the RL on top, it's much more adaptive, and it acts like a controller on top of these individual skills. Okay, and then we have some quantitative evaluation. So here, for our US5 sim in simulation and real, we can see in simulation, BC ordered and RL BC, they perform the same. Why is this the case? Because in simulation, everything is perfect, right? All the skills are exactly the same. Training and test is almost the same. So the ordering and the RL doesn't make a difference. But then if you go to the real, having the RL on top of the skills gets you improvement in performance. And this is in particular true if you look at this breakfast data set and you make current configurations which are harder, so which the objects are closer together, or you have exclusions, and then really having this RL on top of the skills really helps you by a significant amount. Okay, and so in conclusion, we have seen that it's important to design new models for our video, and I think it's also true for robotics, which take into account spatial and temporal information. So it just doesn't just take very simple features, but you have to find ways of how to model the world better. It's not exactly clear what's the best way of training this, what are the best models, but you really have to have some kind of more intelligent models. Then we have seen that weak supervision starts to work. It has been important for a long time, but it was very difficult to get to work. And now with this lot of training data, better features, better detectors, we actually can get to work better. And so basically this is like an interesting thing to explore. Then we have also seen that cross-modal integration by training works. So there was this video bird. And then the last part was learning by interacting with the world. So this is like another new line of research. And what's important there is having more complicated learning approaches give better results, and B, what's necessary there still, I think, is to improve the perceptual model. So basically here the perceptual model is just this simple input of a simple CNN, and what we really want to do in the long term is to capitalize our knowledge about video and learn from video how to learn these representations and how to learn a better structured model, and then we can probably perform more complex tasks and make it more simple to generalize without having all these different tricks to do. Okay, thank you for your attention. If you have any questions.
So thanks for the talk. It's very good. Engineering probably is the only discipline we can get away wherein pouring cereals into a bowl is complicated by saying that. And the reason, I think, is because we stress a lot about correlation, and we've known how to do this, and we continue to do this. Are we looking at the wrong direction for intelligence is my question for you. What would you suggest apart from correlation towards intelligence? Has there been any great work we should be aware of for that?
You mean intelligence as of what kind of intelligence are you referring to?
I don't know the kind, but I mean, even things like, so if you have to execute the task of pouring water into a bowl and not use a lot of training data for that, how would you go about that? I mean, how do you solve it differently is my question.
So I think one thing is like intelligence in general. I think I cannot answer the question because we don't know. And what I can say is like basically how to make systems better is basically leverage the amount of available data to learn from this, right? So basically what you would want to do, what I would want to do is take a video as input, as we saw for this video bird, take a video as input and learn from the video, and then the robot show it to the robot, and the robot can, for example, execute the task, right? So I think one way towards intelligence is to get rid of all this amount of labeled data, all the synthetic supervision, and just like learn on the fly by using self-supervised learning. Or you could say, I do some self-supervised learning with the robot, I let the robot just explore, and then it learns by itself how to grasp things. So, I mean, this is like, that was my initial goal, but obviously it's very hard. But basically for the video now we get it to work, right? So basically we can just use the video data and let the algorithm explore the data and then it learns something. And that would be, I think, in the long term, I think we have to go towards more like self-supervised or weakly supervised learning mechanisms. Otherwise we just sit there and label every and each object, and then the robot arm changes. And then obviously, I mean, robots, if you change the arm configuration, you have to just regenerate all the data right from scratch. So there, it would...
A new shape then, yeah, the whole thing changes. But okay, I'm not aware of self-supervised.
Yeah, I think self-supervised would be, for me, the next step. It's not, I'm not claiming it will be intelligent, but it would be getting rid of some of the annotations, right?
Okay, I think we have some questions in the second room. Can we get questions from there?
Thank you for a great talk. I have two questions about the video BERT models. The first question is that why did you tokenize the video features? Like, what prevents you from using the continuous video features? And the second question is that it seems like you use a mask sentence for the input and then predict the mask word in the output of the text one. So my question is, like, why don't you try like using the first word of the sentence as the input and predict the whole sentence after that?
Okay, so let me go back to the first question, which was why do we cluster, right? So basically the clustering we did to have the same, to be able to apply the same model, which we apply to language to video, right? Basically for language, they have this 30,000 words as input, and then they apply this BERT model. So if you want to apply it as is to video, we have to also do the clustering. And so now what we found is actually, and this is like current work, is that the clustering abstracts away a lot of information, right? So basically language, the words, they're actually clustered by definition, while on video, our space is continuous, and if you cluster the space, we lose a lot of information. So basically, if you want to then use these features for classification, actually we have a big loss in performance. So what we're doing now is replacing this masked objective with other objectives to see if we can have a continuous input and still measure something, because what we have to do is we have to learn the performance. Like, so have to have some constructive loss to measure how this performs, and then use this to propagate and learn information. So yes, basically we're currently working on this. And then the second question was, what was the second? Now I forgot. What was the second question?
Can you use the first word to predict the rest of the sentence? What was that?
Yeah, I mean, basically, if you change the training objective, I mean, it's just you could obviously use it, but then basically the system doesn't. I mean, that's kind of from the BERT. You have to look at the BERT paper, and there, if you just use the first thing to pick the full sentence, you could do this. You can also use sentence prediction. You can use the first sentence to predict the second sentence. That's something they use in the BERT model as well. But basically, it's just if you have not enough information, it's much harder to train. I guess you can do it, but then it seems to be difficult to train the whole system.
Okay.
Thank you.
Okay, are there any more questions?
Yeah, there was a second question from the other room. Here we go.
Yes. Thank you a lot for the call. Actually, I have two questions too. Sorry for on the video understanding part. So, first question is: so can you say something about inference time performance, especially in the video BERT model, and also I don't know your newer work CBT that is always transformer based, because actually with the application you talked about, like safety and security, real time is quite could be quite an important thing. And I don't think we are quite there yet, so how far we are from that?
Well, I mean, basically you have two things, right? You have training and testing. So basically during training, obviously it's not real time, but we don't care. But what we then have to see is how fast it is during testing. And during testing, it's actually not that slow, especially what we showed recently is that we can actually use less layers in the transformer and then basically have the feature extractor and then the transformer. And the transformer doesn't add that much complexity to the feature extractor. So I think you can actually have a downscaled version which runs in whatever, more or less real time, or at least it's not super complicated. While the training takes days, right? So, but that's not the same thing as the testing, and testing is quite quick.
Any more questions? Yes, from this room.
You talked about graph convolution networks a little for activity recognition and seeing the temporal region, but I wanted to get your views on ontology graphs, knowledge graphs, and semantic graphs, because I've seen some papers on these kind of hybrid systems where on one side the qualities of deep learning are being utilized, on the other side semantic graphs are being utilized, and these kind of hybrid systems are getting into understand existence as far as visual scene understanding is concerned and reasoning is concerned. So what are your thoughts on that?
I'm not sure what precisely you're referring to as using simultaneously visual features and ontology features, or what is the...
I'm saying that on, let's say you're using neural networks for training classifiers and understanding the visual components of a scene, and then to make the system capable of reasoning about all those individual components, whether spatially or temporally, you might go for using some kind of knowledge graphs or generating some knowledge base and then querying that.
Basically using the knowledge base as an additional knowledge, like similar to the language information. So I think this is like people are looking into that, how they use the knowledge graph, especially if you have this open vocabulary questions, right? How do things relate? And that's something, it's clearly an interesting research topic, and what I would say, these knowledge graphs, there's a lot of information still missing, right? Because it's so complex that somehow if you look at them, I mean, they have all these entities, but if you look at actions, there are not that many actions in there, right? Because there you really need, and that's the difficulty of actions, that you really need this vocabulary, this large vocabulary of different types of actions, right? And that's something, at least to my knowledge, I would say it's not in the knowledge graph as of today. But, I mean, I'm not an ontology expert, so I don't really know.
Thank you.
Okay, I think we have to finish taking questions now. Thank you very much, Cordelia. Let's thank her again.